In this lecture, I am going to start the discussion with electrodynamic meter movement mechanism. Now, this meter movement mechanism is almost similar to the PMMC meter movement mechanism, but with slight difference. That the first difference is that the permanent magnet in case of PMMC, in this case, is replaced with an electromagnet, you can say. As you can see in this figure, there are two fixed coils, one over here, one over here, according to this figure. So these two fixed coils are going to produce the magnetic field necessary to generate the torque in the moving coil. So in between these two fixed coils, the moving coil will be placed. So the magnetic field produced by the fixed coils and the current which is going to flow through the moving coil, depending upon their interaction, the moving coil is going to experience some force in a particular direction. Now, first of all, let's say that how the movement of the moving coil will take place in this case. So let's say that these are the two meter terminals. Now here we can connect some DC supply, you can say. So if some DC supply is connected such that the current is flowing in this direction, then according to the windings in the fixed coil, the current is going to flow in this direction. And also in this, through the moving coil, you can see that the winding pattern in the moving coil is done in the opposing manner. So whatever the pattern is followed for the fixed coil, the winding in the moving coil is done in the opposite way. So if the current is flowing in the upwards direction here in the fixed coil, then it is supposed to flow in the downwards direction in the moving coil. And again, when the same wire is coming or winding is coming into the other fixed coil, the winding pattern is again same with the first fixed coil. So here the direction of current will be same as well. So considering that, like, okay, a voltage source is connected with this polarity, this is the direction of current flow, and according to the direction of current flow in the fixed coil, you can use the right hand thumb rule to determine the polarity of the electromagnet. So for the first case, if you apply the right hand thumb rule, this portion would be the north pole, this would be the south pole, and as the winding pattern in the moving coil is reversed, so for this case, if you again apply the right hand thumb rule, then this would be the north pole, this would be the south pole, and going to the next fixed coil, again considering the direction of current, the right hand thumb rule can be used to determine the north and south poles. So this south pole and south pole will oppose each other, this north pole and north pole will oppose each other. So there is supposed to be a movement in the moving coil. Now, let's say due to the interaction of the magnetic fields and the current carried by the moving coils, now the direction of the pointer movement is in the right hand side, or in the clockwise manner. Now let's say if the polarity of the supply voltage is changed or it is reversed. Let's say the polarity of the voltage is reversed. Now this is the positive terminal of the supply, this is the negative terminal of the supply. So now the current will start flowing in the opposite direction, or we can say that the current will flow or enter through this terminal and leave through this terminal. So the direction of current will change, in the overall direction of current will change. So now with the reverse polarity, this fixed coil will have a current in the downwards direction as indicated by the green arrows, and okay, let me remove the previous arrowheads. And in the fixed coil, the current direction would be downwards. In the moving coil, as the winding pattern is reversed, the current direction will be in the upwards direction. And again, when we reach this other fixed coil, the current direction will again be downwards. So again, similarly, we can apply the right hand thumb rule to determine the north and south poles. So this would be the north and south poles for the fixed coil. This would be the north and south pole for the moving coil. This would be the north and south pole for the other fixed coil. So now here as well, the north pole will repel each other, south pole and south pole will repel each other, and in this case also the pointer will have a deflection due to this interaction between the magnetic fields developed by the fixed coils and the moving coils. Now for this case also, as the moving coil is uh, experience some force, it is supposed to get deflected. So for this case also it is going to get deflected in the right hand side. You can also try to apply, for both the cases you can try to apply the Fleming's left hand rule to determine the direction of force, and you'll see that for both the cases, whether the polarity of the voltage source is connected in this manner on the previous or in the manner it was connected the first case, for both the cases the deflection of the pointer will be in the same direction. So apart from DC source, even if AC source is connected, this sort of meter movement mechanism, without the help of any rectifier, they can cause the pointer to move in only one direction, because the change of polarity or the change of current direction doesn't change the direction of movement of the pointer. So easily this sort of meter movement mechanism can be used for both DC source and AC source. Now let us try to write the expression of torque for this sort of meter movement mechanism, the expression for deflecting torque. Now, first of all, let us consider that I1 is the current going through fixed coils. So the magnetic flux density produced by the fixed coils should be proportional to this current, because this current is going to magnetize the fixed coils and produce the magnetic fields. So unlike the permanent magnet, where the permanent magnet is producing or providing the magnetic flux lines, here the current is which is flowing through the fixed coils is going to develop the magnetic field lines. So the magnetic flux density would be proportional to I1. Let us just assume a proportionality constant and just write it as k into I1. Now let's say that I2 is the current flowing through moving coil. Although as per the construction discussed in this figure, the fixed coil and the moving coil current is the same for this particular type of construction, but there are electrodynamic meter movements where the fixed coil and moving coil currents are also separate. So let us keep our discussion like this, that I1 is the current through the fixed coil, I2 is the current through moving coil. Now let us say that this is a single turn of the moving coil. Now the coil arrangement, the spring mechanism, and the overall coil arrangement along with the springs and the pointer is almost identical for the electrodynamic meter movement, like it was discussed in case of a PMMC meter movement. So if we consider a single turn coil having the length L and breadth of B, then the force experienced by this single turn coil, or let's say for a single turn the force is force experienced would be F equals B I2 into L, as we have considered that I2 is the current flowing through the moving coil. Now for n number of turns, then the overall force experienced would be NB into I2 into L. So N will represent the number of turns of the coil, and L is the length of the coil. Now apart from that, we have also defined B as the breadth of the coil. Now if we now want to represent the deflecting torque, then we can represent it in terms of the force and the breadth of the coil. So that would be total deflecting torque TD equals F into B. So F can be replaced by N into B I2L, and B, the magnetic flux density, was represented in terms of I1 with a proportionality constant K. So if we replace that, then we can write K into K I1 I2 L into B. Now for this figure which was shown, the current I1 and I2 is the same, the current flowing through the fixed coil and the moving coil. So if we consider that I1 equals I2 equals I, then the deflecting torque can be represented as K N K to A into I square. So A is the effective area, which is equal to the length multiplied by the breadth of the coil arrangement. So now if we look into this expression of the total deflecting torque, then we can see that N, the number of turns, then the area of the coil is fixed for a particular coil arrangement. Once a coil has been formed, then the number of turns and the effective area of the coil is fixed. And K has already been considered to be a proportionality constant associated with the magnetic flux density. So if all these three terms are constant, then it can be said that the deflecting torque is proportional to the square of the current flowing through the fixed and the moving coils. So as it is proportional to the square of the current, then one thing can be suggested from this relation, that the deflection that is going to take place due to the deflecting torque, so that deflection would have a non-linear nature, because it is dependent on the square of a term. So it is not directly related to the current, that is, as it is related with the square of the current. So the deflection resulted through the deflecting torque is going to be proportional to I square as well, and that would result in a non-linear pattern in the deflection. So the scale that needs to be uh, calibrated for this sort of meter movement mechanism, so that scale might have to be calibrated in terms of a non-linear scale. Now, like the PMMC meter movement mechanism, here also hair springs are attached with the coil arrangement, which produces a controlling torque. So controlling torque is produced by the spring, and it is again proportional to the deflection theta. And uh, like previously discussed, the controlling torque can be represented in terms of the spring constant k into theta. Now, at equilibrium, it can be considered that the controlling torque is equal to the deflecting torque. Now, here, for simplicity, we are just considering the controlling torque that is providing the necessary uh, 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 what should I say, the necessary torque to bring the pointer back to the initial position. Now, if we move forward with the discussion, and regarding uh, 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 how the damping can be ensured in this sort of meter movement mechanism. So the damping is normally done in terms of uh, um, by mechanical means. So mechanical damping can be ensured by introducing aluminum vanes, uh, and placing the vane into enclosed air chamber. So like shown in this figure. So like I have written over here that mechanical damping can be introduced by means of attaching aluminum vane with the coil, so that aluminum vane will also move inside an enclosed air chamber. So like shown in this figure, you can see that aluminum vane is shown in the figure that is attached to the shaft of the moving coil. So when the moving coil is going to rotate, it is going to rotate the pointer, as well as when the pointer rotates, as the aluminum vane is also connected uh, with the shaft. So the aluminum vane is also going to rotate uh, along with the pointer movement. Now, this aluminum vane is placed inside an airtight damping chamber. So, this chamber contains some air enclosed inside this chamber, and it is covered with a top. It is sealed with a top covering, so that air is sustained inside the chamber. Now, this produces air chamber damping. Now, when the pointer is, let's say, moving in the right or moving in the clockwise direction, what will happen over here, that the aluminum vane also is going to move in the rightwards direction or in the clockwise direction. But as the air is present inside this enclosed chamber, the air is going to produce some resistance or resistive force into the aluminum vane. So if the aluminum vane tries to move in the clockwise direction, the air present in the chamber is trying to restrict the movement by producing some pressure on the vane. So it has to move in the clockwise direction against the force that it is experiencing by the air present in the chamber or inside the chamber. So as it has to work against the force of the air, some sort of damping is uh, uh, ensured through this mechanism. So the pointer cannot rapidly or abruptly jump from one point to another. Rather, due to the restriction that the aluminum vanes are experiencing, the movement of the pointer will be gradual or slow compared to before. Now, the springs are also producing some opposing torques. Along with that, introduction of the damping mechanism through aluminum vanes can also work as additional damping mechanism. Now, this sort of aluminum vanes can be uh, uh, considered to be analogous to the vanes or blades or of a wind turbine, let's say. So, like when air is uh, uh, passing through the vanes of a wind turbine, the vane is experiencing some force. So similarly, as the vane over here tries to move inside the air chamber, the air is trying to push it back in the opposite direction due to the pressure that it exerts into the aluminum vane. Now, regarding the calibration of the scale of this type of meter movement, the scale is normally calibrated in terms of the RMS values of sinusoidal signals. So that actually makes it sufficient to measure both DC and AC signals, because the RMS value of a DC signal is actually the DC value itself. So if the scale is calibrated in terms of the RMS value of the sinusoidal signals, the same scale can be used for measuring both AC and DC quantities. Now from that, we can suggest some advantages of this sort of meter movement mechanism, that this uh, these sort of meters can be used for measuring both ACs and DC without the necessity of any rectifier circuits, and also the scale can be calibrated directly into RMS values. Now about the disadvantages of this sort of meter movement mechanisms is that the scale might be non-uniform, and also the coil, the current supplied to or through the coil has to be limited to tolerable value, because if excessive current is flowing through the coil, that will cause the coil to heat up, and if the coil is getting heated up, that will change the resistance of the coil. So if the resistance of the coil is changing, then the amount of current that it is going to draw from the supply will also change. So for that reason, the supply of the current has to be limited through the coil of this sort of meter movement mechanism. Now we are going to discuss about electronic analog DC voltmeter. So in electronic analog DC voltmeter, some input switching and range selection circuit is uh, 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 associated, which is based on using electronic components, and also some amplifier circuit is used to amplify the input signal. And for those input range selection and amplifier circuits, electronic components are used, and later on that is associated with the uh, basic construction of DC voltmeters that has been already discussed in previous lecture in terms of a multiplier resistor and the PMMC movement mechanism. So this portion on the right hand side of the terminals A and B is actually identical to the basic DC voltmeter construction that has already been discussed. Now further, this arrangement is modified by associating this basic design with the input range selection and amplifier circuit constructed using electronic components. So that basically allows to increase the sensitivity of the voltmeters and also it allows to have a high input impedance for this sort of meters. For example, using a conventional PMMC meter movement mechanism, let's say a PMMC coil mechanism that has an internal resistance of 100 ohms and uh, rated current of 50 microamperes. So without any additional arrangement, the minimum amount of current that can be measured using this sort of moving mechanism is microampere. So any current less than this cannot be measured using this sort of PMMC meter movement mechanism. Now again, using the same set of rated values, the maximum voltage, the minimum voltage that can be measured is, if we multiply these two quantities, that would be 5 millivolts. So if it is necessary to measure below this value, it would not be possible to measure using this PMMC arrangement unless there is some modification done in the input side. So that modification can be done in terms of introducing this input switching and range selection and amplification circuits in terms of electronic components. So for the construction of these electronic analog DC voltmeters, our main focus would be about the construction of these two blocks on the left hand side of points A and B, that is the input switching and range selection block and the amplifier block, how this portion can be implemented, because the portion on the right hand side, the multiplier resistor associated with the PMMC meter movement, that has already been discussed while discussing the basic DC voltmeter construction. Now, the second figure in this slide is representing a typical switching and amplifier gain selection circuit associated with an electronic analog DC voltmeter. So here there are several switches, as it can be seen that there are two mechanical switches indicated in this figure, S1 and S2. There are a few electronic switches, those can be MOSFETs, that are represented here in terms of S3, S4, S5, S6, S7. So let's say these are electronic switches, these are mechanical switches, S1 and S2. And combination of these switches are going to be, allowing a user to have different output gains. So as you can see that a gain of 1, 10 or 100 can be obtained, and that can be obtained using different combinations of these switching devices. So that will be discussed a little bit later. And this operation amplifier is basically going to serve the purpose of an amplifier, and this sort of an coil arrangement is basically going to provide the application of the amplifier in terms of an non-inverting amplifier. So in previous discussions we have discussed about inverting amplifiers, but in this particular circuit the amplification usually takes place in terms of a non-inverting operational amplifier. Now to further proceed the discussion on how this input switching and amplifier gain selection circuit works, now we are going to consider some constraints along these two terminals A and B, because the portion that is on the right hand side of these terminals A and B, the multiplier resistor and the PMMC meter, we are considering this portion to be fixed. So we have to supply a fixed amount of voltage or current across that portion of the that portion of the voltmeter circuit. So let's say if we consider the portion on the right hand side, there is supposed to be a multiplier resistor RS along with the PMMC meter movement mechanism. Okay, so for our case, we are going to consider that this multiplier resistor and the PMC meter movement mechanism is designed in such a way that a voltage of up to 1 volt can be measured, or a voltage of up to 1 volt can be allowed across the terminals of A and B. So how the multiplier resistor should be chosen for a particular PMMC arrangement in order to obtain a range of 1 volts, that has been discussed while discussing the basic DC voltmeter. Let's say, considering that discussion, the range has been set to 1 volt. So we have to keep in mind that at terminals A and B, whatever the input gain is selected, the output at the terminals A and B can never be more than 1 volts. So that is one constraint that we are going to consider for this particular analysis or this circuit design. And for the basic DC voltmeter arrangement, we have considered that it is tuned up for 1 volt range, but using the input switching and range selection circuit that has been implemented over here, using that input ranges of 10 millivolts, 100 millivolts, 1 volt and 100 volt can be obtained. So using this switching and amplifier gain circuit, these different ranges of the voltmeter can be obtained. So it can be used to measure voltages from 0 up to 10 millivolts, or if the range is changed, it can be used to measure from 0 to 100 millivolts, or from 0 to 1 volts, 0 to 100 volts. So the ranges can be changed in this portion on the left hand side of the terminals A and B. Now we are going to try to consider that how the ranges are going to be selected and how the gains are going to be tuned accordingly to obtain a 1 volt signal at the output of the terminals A and B. So first of all, we can consider the case of 10 millivolts. So before we do so, let us consider one more thing, that the switches S1 and S3, these two switches are closed when the user wants to measure input voltage less than 1 volts, and switch S2 and S4 is closed when the user wants to measure input voltage greater than 1 volt. So considering this thing in mind, if it is necessary to measure a 10 volt voltage in the range up to 10 millivolts, first of all, switches S1 and S3 is going to be closed. If these two switches are closed, then let's say this portion of the circuit is not going to be having any effect for the time being. So whatever the signal is across the input terminals, the DC signal, that is going to be passed towards the non-inverting terminal of the op-amp. So let's say at this point of the terminal, let's say that we are having a signal of 10 millivolts. But our circuit to the right hand side of the terminals A and B is designed for receiving a signal in the range from 0 to 1 volts. So this maximum range of 10 millivolts in this case has to be somehow converted into 1 volt, and that is to be done by choosing the proper gain of this amplifier. So in order to convert this 10 millivolt into 1 volt, the gain that should be selected here is this one, 100. So if we multiply 100 with 10 millivolts, ultimately we will end up with 1 volts at the output of the amplifier. How? Because as I have already mentioned that this uh, uh, op-amp circuit is actually going to work as a non-inverting amplifier, and for choosing a 100 gain of 100 we have to close this switch S7. So if we close S7, we're going to get a gain of 100. So in that case, if I just draw the portion of the amplifier circuit, how it would look like, let's say at the non-inverting terminal we have 10 millivolts, and as switches S5 and S4 are open, we can omit that portion from our analysis, and S7 is closed. So S7 is closed. So the resistances above S7, the summation of these two resistances, let me draw them as separate resistances. This is 90k, this is 9k, and here we have 1k. Let's say this is let's say this is terminal A, this is terminal B. So here for the non-inverting amplifier, the output across A and B, let's say if I write it as VAB, it would be equal to 1 plus RF by RI into BI or V in. So here V in is equals to 10 millivolt and 1 plus RF by RI. So here the feedback resistance RF is equal to the summation of this 90k plus 9k, so that is 99k, and the value of RI, so the summation of these two is RF and this is RI. So according to this expression, we can write it to be 99k by 1k into 10 millivolts, which eventually will give us a value of 100 multiplied by 10 millivolt. So in this case, after closing switch S7, we are getting a gain of 100. And if we multiply 10 millivolts with 100, then at the output side of the amplifier across terminals A and B, we're going to have an output voltage of 1 volts. That is the rated voltage for the multiplier resistor and the PMMC combination for the DC voltmeter. Now, if we consider another case, let's say the case of 100 millivolts, because for this arrangement we said that it is going to work for 4 different ranges: 10 millivolts, 100 millivolts, 1 volt and 100 volt. So these are the maximum ranges. Now when a particular range is selected from 0 to up to that value, any in between values can also be measured. So for 100 millivolts, as it is less than 1 volts, for this case also we have to close S1 and S3. Then for 100 millivolts from the gain selection portion of the amplifier, we have to select a gain of 10 in this case. So in this case, S6 has to be closed as well. So again, the amplifier circuit would be, okay, I think it is not necessary to draw the amplifier circuit, but if I only consider the gain, what would be the gain? It would be 1 plus Rf by Ri, so 1 plus 90k, which is Rf in this case, and Ri is the summation of these two resistances, that is 10k. So eventually we'll have 1 plus 9 equals to 10. This would be the gain in case of 100 millivolts, and eventually at the output side we are again going to end up with 1 volts. Now let us consider the case of the input voltage range of 1 volt. So if you want to measure any signal between 0 to 1 volts, so for that, like it was mentioned in previously, that for less than 1 volts we have to close S1 and S3. For greater than or equal to 1 volts we have to close S2 and S4, these two switches. So here S2 and S4, these two switches are going to be closed, and S1 and S3 in this case are going to be remaining open. So this branch is not going to have any effect now in the operation of the circuit. Rather, these two lines are going to be shorted because these corresponding switches are closed, and these two resistances R2 and R3 are going to form some sort of a voltage divider. So the input voltage of 1 volts is going to be divided through this voltage divider, and the respective respective voltage dropped across this 100k resistance is going to be supplied to the non-inverting terminal of the op amp. So here if the voltage divider is considered, let's say the voltage that is coming over here, let me denote it as Vn, let's say. So what would be the value of Vn? It would be equal to R3 divided by R2 plus R3 into Vn, the input voltage that is considered to be maximum of 1 volts in this case. So this combination is going to actually scale down the input voltage by a certain amount. And what will be the amount? So in this case it would be 9.9 mega ohms divided by 9.9 mega ohms plus 100 kilo ohms multiplied by Vn. So this scaling down factor or the attenuation factor would eventually be 1 by 100. So although the input voltage here is considered to be 1 volts, it is going to be scaled down by a factor of 100. So if the input voltage is getting factored out by 100, then proper gain should be chosen from the three available gains of 1, 10 or 100 to ensure that the output side at A, terminals A and B, we can ensure a signal of 1 volts. So if 1 volt is applied at the input terminals, it is scaled down by 100. So again, in this gain selection portion of the amplifier, a gain of 100 should be selected. So the switch S7 should be closed in this case. So it will again amplify the signal by 100 times, and eventually at the output side we are going to get an input voltage of 1 volts. Now lastly, if the 100-volt case is considered, so again S2 and S4 are going to be closed in this case, and the scaling down factor of these two combination of resistances are going to cause the 100-volt signal to be scaled down to 1 volts. So 1 by 100 to 100, so it will scale down the input voltage to 1 volts at the input of the open. So if a gain of 1 is selected in this case, so if S5 is closed in this case, that would be sufficient to provide an output voltage of 1 volts across the basic multiplier resistor and the PMMC combination of the DC voltmeter. So like seen over here, that although on the right hand side of the terminals A and B, a multiplier resistor along with the PMMC was designed to obtain an maximum input voltage range of 1 volts, but using the electronic switching and amplifier gain selection circuit, that range can be further enhanced into smaller scales and also in larger scales. So for this particular arrangement, starting from 10 millivolts to 100 millivolts to 1 volts and even 100 volts, these different possible ranges can be obtained. So by changing the input resistance combination of the voltage divider at the input side, or changing the resistance combination on the amplifier portion, multiple different gains can be obtained and different ranges can be also obtained for measuring voltages of different magnitudes. So clearly the basic circuit, which was designed for 1 millivolt, the sensitivity of this basic DC voltmeter design was enhanced by reducing the minimum amount of voltages that could be measured using the same arrangement by introducing the electronic analog voltmeter portion. Now it might happen that in a particular application, it is needed to design an voltmeter that needs to be having the option of different input voltage ranges, such as 20 millivolts, 50 millivolts, let's say 100 millivolts, 10 volts, 20 volts. So for these sort of combinations as well, a similar circuit can be formed, and for obtaining these different input voltage ranges, it might be necessary to tune this resistance combination at the input side, or tune this resistance combination on the output side. So for these 4 ranges, it was sufficient to have 3 different gains of 1, 10 or 100, but for these different combinations, it might be necessary to even have further options of selecting different gains of this amplifier circuit. Okay, so just for an example, let's say this circuit that is designed for having these different input ranges, input voltage ranges, 10 millivolts, 100 millivolts, 1 volts or 100 volts. Let's say we also want to add another input voltage range, that is 20 volts. So this additional option to give the option of measuring from 0 up to 20 volts using the same arrangement of the typical switching and amplifier gain selection circuit. Let us see that where we have to do some changes or some modification. Let's say as 20 volt is greater than 1 volt, we can close the switches S2 and S4. If these two switches are closed like before, this branch will be ineffective and this branch will be dividing the voltage into scale down the voltage by 100 times. Let's say 20 volts is considered along these two terminals. So this voltage divider is going to divide the voltage into 0.2. So 0.2 volts is getting supplied at the non-inverting terminal of the op-amp. So as our terminals A and B has to have a voltage of 1 volts, maximum voltage of 1 volts. So this 0.2 volts has to be converted into 1 volts using the amplifier. So a gain of 5 is necessary in this case, because if a gain of 5 is selected through the amplifier, 5 multiplied by 0.2 volts would eventually give a 1 volt signal at the output of the amplifier. But currently the arrangement that we are having over here, that is not sufficient to provide a gain of 5, because this arrangement are providing 3 different gains, 1, 10 and 100. So the total resistance over here, the combination of R4, R5 and R6, we have a total resistance of 100 kilo ohms over here. So we can try to subdivide this distribution of the resistances to create another branch that is going to generate a gain of 5. So for that, let's say first of all, if we consider the formula of gain, that is 1 plus Rf by Ri, then how we can distribute this 1 kilo ohm resistance to get a gain of 5? So this ratio has to give me 4. So 1 plus 80k divided by 20k would actually give me 1 plus 4 equals 5. So if we can design the non-inverting amplifier such that I have 80k as my RF and 20k as my Ri, then it would be sufficient for me to obtain a gain of 5 for this non-inverting amplifier. So what we can do, we can create a branch over here. We can add another MOSFET. Let's say I am denoting it as S8. So instead of connecting a 90 kilo ohm resistance, we can divide it into 2 portions. That is, so one portion can be 80k, another portion can be 10k. So the 90k resistance, we are dividing it into 2 parts. So this branch is now supposed to give me a gain of 5. So when I'm going to close switch S8, from this branch I am supposed to get a gain of 5, because over here this 80k would represents RF and the summation of the rest of the 3 resistances 10k, 9k, and 1k is going to give me 20 ohms, 20 kilo ohms, which is going to be the Ri in this case. So uh, in that sense, the calculation that I have done over here, so I can get a gain of 5. So the gain of 5 is going to be amplifying the 0.2 volts into 1 volts. That is uh, that is I mean the rated voltage that has to be supplied across terminals A and B. So similarly, other voltage ranges can also be obtained, such as 50 volts, or other combinations of input voltage ranges can also be obtained by tuning the distribution of the resistances. So uh, uh, up to this, I would conclude into this particular lecture. So in the next lecture, we are going to discuss about the principle of electrodynamic wattmeter.